Welcome to the Depth Dive. Today we're looking into, well, the ongoing quest to make large language models better at reasoning, for tasks like math or coding. And for a long time, the main approach has been reinforcement learning after the main training, RL.
Yeah.
You basically reward the model for getting verifiable answers right, and yeah, it's led to some really big performance improvements.
Huge jumps. It's been so effective, really, that it's almost become the default thinking, hasn't it? That you have to do this extra RL training to unlock serious reasoning.
Yeah.
But this brings up a really interesting question one of our sources dive into. Is RL actually creating brand new abilities? Or is it maybe just distribution sharpening?
Distribution sharpening, meaning just making the model more likely to use the strong skills it kind of already had hidden away.
That's the idea. Are we just surfacing latent abilities that were there in the base model all along?
Because if that's true, then maybe all that complexity and cost of RL, the training, the tuning, needing those perfect rewards, maybe it's not strictly necessary. And that leads us to our mission for this deep dive, looking at research proposing something called power sampling. It sounds, well, surprisingly simple. A training-free sampling method. It just uses the base model's own likelihoods, apparently, to get similar or sometimes even better reasoning performance than RL.
And that's the key takeaway for you listening. Understanding this could mean getting really strong reasoning performance without needing, complex training setups, special data sets, or reward systems. It's all done at inference time.
Okay, so let's get into the mechanics. The sources say it's inspired by MCMC Markov chain Monte Carlo methods. How does that work? How does MCMC help sample better?
Right, so the goal isn't to sample directly from the model's original probability distribution, let's call it P. Instead, they want to sample from a mathematically sort of amplified version. They call this the power distribution, P to the power of alpha, or pay alpha. Now, technically, this alpha isn't a normalized probability distribution, which is why MCMC comes in. You need a method like MCMC, specifically an autoregressive type with resampling, to effectively draw samples from it.
Okay, hang on. Help me visualize that. We have the base probabilities P. What does raising it to a power alpha actually do conceptually?
Okay, imagine the base model's distribution feet like a broad beam flashlight showing all possible paths an answer could take. Some paths are dim, some brighter. The power distribution, PAL-FED, is like taking that flashlight beam and focusing it into a laser. When you raise P to the power alpha, assuming alpha is bigger than 1, you exponentially boost the relative importance of sequences that already had high likelihood. It makes the sampling much, much more biased toward what the model inherently thinks are the best paths.
That sounds promising. But I'm thinking about the trade-off. MCMC, iterative resampling. Aren't we just swapping training complexity for inference complexity? Does it slow things down a lot?
That's a fair point, and we definitely need to touch on the scaling later. But the immediate advantage is, let's say, purity. You're working directly with the intelligence that's already baked into the pre-trained model. You avoid potential instabilities or biases that the RL training process itself might introduce. And it's a simpler mathematical change to the sampling itself compared to navigating the huge optimization space of RL.
Right. And speaking of simpler changes, lots of people use low temperature sampling, LTS, just tweaking that temperature setting. How is this power sampling, this alpha idea, different from just dialing down the temperature?
That's actually the core technical insight here. They look similar on the surface, but the research shows LTS does not mathematically sample from alpha, and the difference really matters for reasoning. Power sampling, drawing from alpha, heavily favors tokens that lead to paths with maybe few, but very high likelihood future steps.
So it's really looking for the most robust, high-quality path forward.
Kind of like planning ahead, yeah. Low temperature sampling, on the other hand, might boost tokens that lead to lots of possible next steps, but maybe none of them are actually that high likelihood overall. For something tricky like multi-step math or detailed code, that distinction is critical. Power sampling helps navigate what the sources call critical windows.
Critical windows. Oh, what are those exactly?
It's like a fork in the road during generation. Maybe choosing a plus or minus sign early in an equation or the first command in a coding loop. Just a few tokens there can decide if the whole final output, maybe hundreds of tokens later, is correct or not. Power sampling tends to avoid paths that look okay at first but lead to a dead end later, probabilistically speaking. It's aiming for global quality by favoring those high likelihood futures.
It sounds a bit like it's doing self-correction or look ahead without explicit training for it. And that gets around needing, the whole RL setup, ground truth verifiers, managing training headaches.
Which takes us right to the results. The no training needed claim is bold. Does it actually stack up against the standard? So they benchmarked power sampling against base models and a common RL method, Group Relative Policy Optimization, or GRPO. These models like Quen 2.5 Math 7b, Phi 3.5 Mini Instruct, and tested on Math, Coding, General Knowledge Math 500, HumanEval, GPQA, plus applicability 2.0 for helpfulness.
Okay, let's start where RL should shine, in domain reasoning, like Math 500 for a math-tuned model. How did power sampling do there?
Impressively close. On Math 500 with Quen 2.5 Math 7b, power sampling got around 0.748 accuracy. GRPO was slightly higher at 0.785, but that gap is pretty small. It shows this inference time method captures most of the gains you get from intensive RL training, at least in the domain the RL was tuned for.
Okay, close on the home turf. What about out of domain, where RL alignment sometimes struggles to generalize?
This is where it got really surprising. Power sampling was about level with GRPO on GPQA, the general knowledge test. But on HumanEval, the coding benchmark, and applicability 2.0, the helpfulness one, power sampling actually beat GRPO, significantly in some cases.
Whoa, okay. Let's highlight that HumanEval result for the Phi 3.5 model. Because those numbers, they're pretty wild. Base model gets 0.213 accuracy. GOPO, the fancy RL method meant to boost things, actually tanks the performance down to 0.134. But power sampling, zero training, gets 0.732. That's a massive difference.
It really is. It strongly suggests that, at least sometimes, RL alignment might inadvertently suppress some general abilities, like a kind of catastrophic forgetting for certain tasks. The potential was still there in the base model, but RL somehow obscured it. Power sampling just found it again, unlocked it.
Incredible. And qualitatively, did the answers look different, like length or style?
Interestingly, no, not really in length. Power sampling outputs were about as long as successful GRPO ones. For instance, on Math 500, Quen 2.5 Math 7b generated around 679 tokens with power sampling versus 671 for GRPO. And that's without any explicit push for longer answers in power sampling. It kind of suggests that solving complex problems often requires reaching a certain level of detail or number of steps. Both methods, when successful, seem to find their way to similar high confidence, high likelihood parts of the model's possibility space. The link between the base model's likelihoods and actual accuracy seems really strong, however you get there. Power sampling just seems to navigate to that good region more reliably in some cases.
Okay, this idea of a shared high likelihood region, it connects to a known issue with RL, right? The collapse in diversity. RL models often give the same answer over and over.
Right. They can become very narrow, which isn't great if you want varied responses or need multiple attempts to solve something. Power sampling seems to avoid this. Because it's working with the underlying probabilities differently, it doesn't seem to collapse everything onto one single best path. You can see this clearly with the pass at K metric. That measures if you get at least one correct answer within K tries.
And the results there.
Very clear. On Math 500 again, power sampling's pass at K score beats GRPO for any K greater than 1. Its whole performance curve is better than both the base model and GRPO, showing it keeps generating diverse, useful outputs. Better for practical use where you might need a few shots at a problem.
Okay, but let's circle back to that complexity point you raised earlier. The inference cost. It's not free compute-wise.
No, it's definitely not. There's a cost at generation time. Because it's doing these iterative MCMC steps, the total number of tokens processed scales up. Roughly with the square of the final sequence length and the number of MCMC steps you take, let's call it non-MCMCO.
So more compute per answer generated, like paying a bit more for a potentially much better result, maybe. Is there a sweet spot for how many steps this an MCMC?
Yeah, they looked into that. For reasoning tasks, they found the exponent alpha $4 seemed best. That's the sharpening level. And importantly, the performance gains tended to level off after about non-MCMC 10 steps. So you don't need endless iterations. A relatively small fixed number of these resampling steps seems enough to tap into that latent potential.
Okay, so pulling this all together, the main takeaway feels pretty significant. The fact that this relatively simple training-free method works so well suggests our base models are maybe much more capable at reasoning than we usually give them credit for.
Exactly. Well, yes, it really shifts the perspective. Strong reasoning might not be something you have to build with expensive coast training. It seems tightly linked to those high likelihood regions that already exist in the base model's distribution. RL might just be one complicated way to find those regions. Power sampling seems to be another, maybe more direct way.
Given everything we've discussed, especially that striking HumanEval example where power sampling succeeded where RL failed, what does this suggest to you about the sheer amount of untapped potential just sitting there in these models, even before we start any complex training?